everyone. My name is Zane D'Angelo, and today we are going to be talking about the Pacific Plate. So what do we know about the Pacific Plate is that it's mostly composed of oceanic crust, with very little continental crust being right over here in this little corner, sort of splitting with the Australian boundary, the Papua New Guinea area. So we know that most of that one big thing that's sort of the defining feature of the Pacific Plate is that it is mainly oceanic, and that it's made up about like 97% oceanic, I'd say. It's covering oceanic crust by a large margin, much more than something such as the North American Plate or the Eurasian Plate or the South American Plate or the African Plate. Just sort of things like that. Other plates that border it, obviously, we have bigger ones, such as the North American Plate and the Antarctic Plate, but we also have smaller ones that aren't as well known, as such as the Australian Plate, the Nazca Plate, the Cocos Plate, and the Juan de Fuca Plate, and the Filipino Plate. All these are just sort of smaller plates that people don't know as well, and would expect them to be, perhaps also a part of the Pacific Plate, but no, these are all the bordering plates of the Pacific Plate. The primary amount of motions that it has are convergent, mostly, following along their northwestern and western boundaries. We're looking, at the North American Plate, at two of them specifically right here, and the Australian Plate right here and right here. This indicates that the Pacific Plate is going northwest, because also due to the fact that there are divergent boundaries right here, and a transform boundary right here, which is where the San Andreas Fault would be. The Pacific Plate moves about 3 to 4 inches or 7 to 11 centimeters a year, which is slow when it comes to us, but when it comes to some other relatives to some other plate, such as the North American Plate, it moves about 4.7 to 8.7 centimeters faster, or about 2.3 or 2 to 3 inches faster than the North American Plate. So we know that this plate is moving fairly fast compared to some of their neighbors, but still, this is a incredibly slow movement for us. So the proof that we have regarding the topography and the movement of this plate is all within this map right here. So as you can see with this meter, anything below 0 and anything in sort of the anything below 0 is below sea level. So typically with the ocean floor is going to be at the sort of like purplish, super dark blue, pinkish color, whereas on the flip side, above sea level is green and brown and gold and white and really, really light purple. So what we can see along this right here, if you're looking at my mouse, is that there are sort of underwater mountains, in a sense, along this plate boundary, where the convergent boundaries are pushing up against each other, causing these mountains to be formed. This sort of a explanation as to why there are smaller chains of islands, such as take Hawaii for example, or this right here, I believe that's not the Aleutian Islands. Anyway, so yes, we see that there are mainly convergent boundaries right along this area, where the elevation of the seafloor is starting to rise up due to the convergent boundaries. Now on the east side of it, this is the San Andreas Fault right here. We see that there is very minimal amounts of sort of underwater mountains per se. We don't really see them as often. This sort of indicates that it's moving away, moving away from its neighbors, not staying connected. We see a little bit of convergence right along here, but that's just about it. So yeah, this is just about all the proof that we need to show that this plate is moving northwest, going up into the Eurasian plate towards Antarctica. Towards the Arctic, I mean. Yeah, that's just about it, though. I hope you enjoyed this video, and have a nice day.